Aloha BioChem. In this lecture we cover the topic of density in Chapter 1. So we are getting towards the end of the chapter. In today's lecture we go through section 1.10, density. So we're skipping over temperature. We'll do that last. And let's do density. So you've probably heard of density before. Density is very closely related to weight. In fact, we explained density in a previous video, but we want to go through it fully in this one. Density is like a description of how heavy something is for its size. So for example, suppose you have a block of iron and a block of styrofoam. They're the same size. Well, which one's heavier? The iron is. So it's more dense than the styrofoam. Okay? So when you have objects of the same size, the heaviest one is the densest one. Now gold is even more heavy than iron. The same size block of gold, it would be even heavier than the iron. So gold is more dense than iron. It's like density is the amount of weight that's crammed into the material. Okay? Now if you have some styrofoam and you want it to be the same weight as the block of iron, well, you need a humongous chunk of styrofoam for it to equal the same weight as that one small block of iron. So iron's much more dense than styrofoam, and all of the materials out there, they all have their own density. So density is a physical property of matter. You can observe it without changing the material into anything else. So it's a physical property. And it relates a substance's mass to its volume. It really tells you how heavy an object is for its size. So let's compare a block of gold, a 10 centimeter cube block of gold, with a 10 milliliter beaker of water. Now remember, a cubic centimeter is the same thing as a milliliter. So if you have 10 cubic centimeters of gold and 10 milliliters of water, you have the same volume of both. When you're talking about liquids, it's more appropriate to use the milliliter term. And when you're talking about solids, you use the cubic centimeter term. Okay, but they're really the same amount. Now, 10 cubic centimeters of gold weighs 194 grams, whereas 10 cubic centimeters or 10 milliliters of water only weighs 10 grams. Look at how much heavier the gold is than the water. Now, water is not that light. It's pretty dense itself, but gold, wow, it's almost 20 times as heavy as the water. The way you calculate density to get an actual number is by taking the mass of the material and dividing by its volume. So that will give you the actual density number or a measurement. So let's do that for these two materials right here. Let's calculate the density of gold and water. So the density of gold would be the mass of the gold, 194 grams, divided by the volume of the gold, 10 centimeters cubed. So when you do mathematics with measurements, let me zoom in a little bit. Remember, you handle your numbers separately from the units. So dividing grams by centimeters cubed, nothing cancels out there, so we end up with grams over centimeters cubed. And that's a unit of density. And the numbers, 194 over 10, you get 19.4. So the density of gold is 19.4 grams per cubic centimeter. You could also say it's 19.4 grams per cc. So cc is another name for cubic centimeter, and in the health profession you use cc's all the time. Give me 30 cc's of saline solution. That's 30 cubic centimeters of saline solution, or 30 milliliters of saline solution. So, okay, 19.4 grams per cc. Now, that's telling you that 1 cc weighs 19.4 grams because it's 19.4 grams per cc. And if you had 10 cc's, you would have 10 times that amount of mass, 194 grams, because each one weighs 19.4 grams. So the density tells you how much one of them weighs. That's how you read this, 19.4 grams per cc. Let's do this for water. Density is mass over volume, 10 grams over 10 milliliters. And so for water, it's simply 1 gram per cc. So 1 gram per milliliter. I think for liquids, it would be weird to say cubic centimeter, but cc is okay for some reason. So 1 gram per cc. I'll just use cc. So water, if you have a single cc, it weighs 1 gram. 1 gram per cc. Gold, if you have a single cc, it weighs 19.4 grams. So it's almost 20 times as heavy as water for that 1 cc. Now, water is very interesting, and the density is kind of convenient because look at the mass of water. When you have 10 grams of water, you automatically know how much volume you have. That's 10 milliliters. And if you have 10 milliliters of water, you know how much mass there is. You have 10 grams. So, water has a convenient density, okay? 1 gram per milliliter. Now, you should note that less dense substances will float on more dense substances. If you take this block of gold, however, and you stick it in the water, it's not going to float because it's more dense than the water. But if you have, say, styrofoam, the density of styrofoam is probably like 0.05 grams per cc. It would be much less dense than water. And if you put styrofoam in here, it would float on the water. Wood is also less dense than water, and so it would float on the water. I'll show you a table of densities here. And we can see which ones might float on the water. So here's a bunch of materials, and there are different densities. Most of them are more dense than water, by the way. These are, aluminum is 2.64 grams per cc, so that wouldn't float. Brass is 8.55. Brick is 1.92. Okay, coal, that's a little bit more dense than water, but it would still sink in the water. Copper is pretty dense. Here you go, cork. The density of cork. You ever wanted to know what the density of cork is? It's 0.24 grams per cc. So if you put that on water, it would float. Gold, wow, yeah, density of gold is 19.29, and what we calculated, 19.4. Okay, so the reported density over here is a little bit less than our density right there. Sometimes you get different, values of density depending on where you look. Ice is a little bit less dense than water, 0.92, so ice will float on water. Okay, and you could look, see all these different types of woods. They're less dense than water, so they would also float. But then, wax, paraffin wax would also float on water. So kind of interesting. Now, there's a table in your textbook, table 1.6, which has the density of a few materials. It even tells you the density of certain gases. So oxygen gas is much less dense than water, 0.00143 grams per cc. Okay, gasoline is also less dense than water, 0.66. So if you put gasoline in contact with water, It doesn't mix with the water. If it mixes with the water, of course, it's not going to float, but, it doesn't mix with the water, and it'll be the upper layer. Just like oil in water. Oil floats on water because it's less dense than water. Okay, and here's some other materials in the body. Urine, slightly more dense than water. Urine's got stuff dissolved in the water, and when you have stuff dissolved in water, it makes it a little bit more dense, tiny bit more dense, like blood plasma. It's mostly water, but it's a little bit more dense than water. Okay. All right, so that's a little bit about density. Now, suppose we want to know, let's do some calculations now. How much volume does 125.5 grams of bone occupy? How much volume does 125.5 grams of bone occupy? So we're given the mass of bone, and we're asked for how much volume is that. I just saw bone over here in the density table in the textbook. So there you go. There's bone. The density of bone is 1.80 grams per cc. So the way you solve for the volume is you take your density equation. Density is mass over volume. And solving for volume, you get volume is mass over density. Okay? Density is mass over volume, so volume is mass over density. You can swap these places right here. And so you plug in the mass that you're given, you plug in the density that's in the textbook, and when you do the calculation, you handle your units separately. So you have grams upstairs, and downstairs you're dividing by grams over centimeters cubed. So the gram cancels the gram, and then the centimeters cubed, you're dividing by centimeters cubed, but it's already in the denominator down there, so it comes back up. And so centimeters cubed will be your unit. So that's good. We were looking for volume. It's supposed to be the unit. You see, when you do calculations with units, you can kind of, it's a good way to check that you're doing it right if you end up with the right type of unit. And then doing the numbers, 125.5 over 1.80, you get 69.72222, and we keep 3 sig figs, so it rounds to 69.7, okay? Because we have 4 sig figs for the mass and only 3 sig figs for the density, so the density limits us in the answer to 3 sig figs. Now, an alternate way of solving this problem is by using density as a conversion factor. When you look at the density of bone, there it is again, 1.80, and the units are grams per cc. That's telling you that bone is 180 grams for every single cc. So 1 cc, 1 cubic centimeter, is the same thing as 180 grams. They're the same thing when you're talking about bone. So we can use this relation to convert from grams to cc's. So take the mass and put it there on the left, and then take the relation and build the conversion factor. We want to get rid of the mass, and we want it to convert to volume. So we put the mass down there and the volume up there. You can't quite see that. Let me turn that off. Okay. So here's the calculation. You start with your mass, put the 1.80 grams down there and the 1 centimeter cubed up there, and that gets rid of grams, and you're left with centimeters cubed, which is what you were looking for. And doing the numbers, 125.5 divided by 1.80, you get 69.7. You're doing the same math here. You're taking, last time we did in the previous method, 125.5 divided by 1.80. In this one, you can see you're doing the same division, 125.5 over 1.80, and There you go. So it's the same answer, two different ways to do it. Okay. Now, another problem. What is the mass in kilograms of 2 pints of blood plasma? You have 2 pints of blood plasma. How many kilograms is that? Now, going back to that table, there was also blood plasma listed. So here it is, bone and then blood plasma. The density of blood plasma is 1.03 grams per milliliter. 1.03 grams per milliliter. So here's that relation. So the density is 1.03 grams per milliliter. So 1 milliliter is the same thing as 1.03 grams when you're talking about plasma. All right, let's turn this off. Now, you have 2 pints. If we can figure out how many milliliters that is, we can use this density relation to convert it to grams. And then once we know the grams, we can easily get to kilograms. So that's what we'll do. Starting with pints, we convert that to somehow to milliliters, and then we go from milliliters to grams and grams to kilograms. All right. Well, looking at one of the author's tables for the common standard English metric conversions. So this is table 1.4. All right, table 1.4, and if you go down to the volume part at the bottom, you can see that, we start with 2 pints. Now, right here I see 2 pints is the quart. And then over here, 1.06 quarts is a liter. And so we know that 1,000 milliliters is also a liter. So let's see if we can put all this together. Now we're starting with 2 pints. We know from the table that 2 pints is a quart. So we can turn pints into quarts using this first relation. And then quarts into liters using this second relation. So this is our English to metric conversion here. We can turn quarts to liters. And then we can turn liters to milliliters using this third relation. And then milliliters to grams using the density relation. And then grams to kilograms using, what we know a kilogram is. So there's 5 relations. So we starting with pint, go to quart, quart to liter, liter to milliliter, milliliter to gram, gram to kilogram. So these 5 relations are going to be strung together as 5 conversion factors, and it'll be one long calculation. So make sure you're stringing them together correctly. Starting with 2 pints, get rid of pints, turn it to quarts. So the 2 pints goes on the bottom, the 1 quart goes on top. And then get rid of quarts, go to liters. So this goes on the bottom and that goes on the top. Get rid of liters, go to milliliters. Get rid of milliliters, turn it to grams. And then finally get rid of grams, turn it to kilograms. And you see how the units all cancel off. And you're left with units of kilograms. And doing the numbers, 2 divided by 2 divided by 1.06 times 1,000 times 1.03 divided by 1,000. The thousands cancel, the 2's cancel. So really all you're doing is 1.03 over 1.06. And you punch that in and you get 0.971698. But we started with 2 sig figs. And everything's exact except for this one and that one. So these are 3 sig figs and 3 sig figs. And so we're going to keep 2 sig figs. What we started with will be what limits us at the end. So our answer is rounded to the 2 sig figs. It rounds right there. So that's 0.97 kilograms. So that was a pretty good example. Now, in the textbook, it mentions specific gravity. So I don't have any notes prepared on specific gravity, but I'll just explain to you what it is. Specific gravity is basically the ratio of the density of a substance to the density of water. So let's go back to the table of densities in the textbook. Okay, so what's the density of water again? You can see right here, table 1.6. The density of water is easy to remember. It's 1 gram per milliliter. Now, what's the density of gold again? Okay, let's go back to that other table I showed you before. Density of gold is 19.3. So gold is 19.3 times the density of water. So basically, you say that the specific gravity of gold is 19.3 times, or is just 19.3, because it's 19.3 times that of water. Density of ivory is 1.84 grams per cc, so its specific gravity is simply 1.84. Copper's density is 8.91 grams per cc, so its specific gravity is 8.91. Okay, specific gravity is just like you get rid of the units. Okay, that just tells you how many times the density of water this density is. Anyway, I'm not going to go much further into specific gravity. I don't really use it much, and probably won't test you on it either. So that's it for this video, and in our next video we will go into temperature. That will be our last one for chapter 1. So stay tuned for that. Aloha.